Number 39. Solve example 21.5 but use loop abcdefgha instead of loop akledcba. Explicitly show how you follow the steps of the problem solving thingamajig, and yeah, we're not going to follow those steps. And the reason being is because we're going to do it. So, before we get started, what I'd like to mention is that for a detailed review of how to solve these problems, check out number 35, 36, 37, and 38. I'm going to go a little faster on this. Otherwise, I'll be in this chapter for the next 7 years. Okay? So what we're going to do is we're going to analyze this circuit. We got to try to find the currents. So the first thing is we're talking about using this particular loop. So A, B, C, D, E, F, G, H, A. All right, so we're going to be analyzing. They want us to use that loop now. So let's just apply loop rule for that. Okay, so we got to apply loop rule. Remember, loop rule just simply says that the sum of all of the potential rises minus the sum of all the potential falls is equal to 0. Okay. All right. So now I'm going to use the currents as stated here. All right. So since we're analyzing this in a clockwise fashion, and it's showing that the current is moving in a clockwise direction at the top, I know that every time this current flows through a resistance, it's going to represent a potential fall. Okay. So in the potential falls category, so let me set this up now. I'll put like two. I'll probably need a little more space. Actually, you know what? You know what I'm going to do? I'm going to move this up here a little bit. Oh, there goes the picture. I'm going to move that up here. All right, and I'm going to start writing it. So here, minus dot, 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 equals 0. All right, so the potential fall here is going to be I2, right? Remember that we're using Ohm's law. V is equal to IR. So to find the potential drop across this, I need to know the current and I need to know the resistance. So it's simply going to be the resistance of 2.5 multiplied by the current of I2. So I'm going to write 2.5 times I2. Great. And now I move on to the next one. All right. So now we're going to go through the battery, and look, anytime you go from a smaller line in a battery to a bigger line, remember the bigger line represents the positive. You're going from positive to negative. You're becoming happier, right? So that is a potential rise. That represents a potential rise. And so you're going to write that down in this category, 18. Okay. That's the potential rises. Then we're traveling along. Up, we hit another resistance. So this time it's going to be the resistance of 0.5. So I'm going to add it. The reason why I'm adding them is because I'm subtracting all of them at the end. So please don't plug in a negative there and subtract it, because then it'll be totally wrong. So what we're going to do is we're going to do 0.5 times then I2. All right, great. And now we're traveling we're traveling around, and here we go. So now the stated current is going in the opposite direction of how I'm analyzing this. Now what that means is that this now will represent a potential rise. So what I got to do is go into my potential rise category and add into it my resistance of 1.5 times then I3. Okay, easy enough. So we're traveling along. Up, we hit another resistance, but we're traveling opposite to the stated current. So that's going to go in the potential rise category. So that's going to be 0.5 times I3. All right. I'm going to need a little more space. I just need more space, man. It's not you, it's me, I swear. So here, now what we're going to do is we're going from positive to negative, right? So we're becoming sadder, right? We went from a positive state to a negative state. So anytime that happens across a battery, it's always going to represent a potential fall, right? You're falling in potential. How much? 45 volts. They gave it to us. So you're literally just going to plug that in here under the potential falls category. And finally, we go back to point A. Okay, so we're done with analyzing that loop. All right, so this is the full-blown equation. Now we don't need any more room here, so maybe I'll tidy that up. And what we're going to do is we're going to, what am I doing? Yeah. What we're going to do now is we're just going to kind of simplify stuff, add some like terms. So we've got two I3s in there, right? So that's actually going to work out to 2I3. That's interesting. So that's 18 now, plus 2I3. All right, minus then, this stuff, we'll combine some I2s in there. So it looks like we're going to have 3I2 plus 45 is equal to 0. Distribute the negative now. So there's how the negatives work out. All right, so plus then 2I3 minus then 3I2 minus 45 is equal to now 0. All right, and then all we're going to need to do here is we're just going to simply have to take 18, and then we're going to subtract from that the 45, and what we're going to get is a negative 27. So we realize that we're going to have 2I3 minus 3i2 minus 27 is equal to 0. All right, so leave this equation on over, on the side somewhere. All right, let's leave it maybe up here. All right, so leave that alone. Now what we're going to do, though, is we're going to need another loop, okay? Anytime you're analyzing a circuit like this where you got 3 currents, almost always you're going to have or apply 2 loop rules, and then you're going to need a junction rule. All right, so we did 1 loop. What loop do you want to do next? It doesn't really matter, but it can't be the loop we just did. So maybe we'll choose now this loop, and we'll go in this direction. And did I have to go in that direction? Could I have analyzed it this way? Of course I could have. It doesn't matter. You just have to be careful when you're plugging in rises and falls. Everything will make sense at the end. Okay, so don't overthink it. In the beginning, just choose a loop. And just choose a place to start and a place to end. I'm going to choose it this way just because I'm moving in the direction of the current, so maybe it'll just be a little easier, but it really does not matter. All right, so same thing. I'm traveling now with the current here going through resistance number 2, so I know that that's going to represent a potential fall. So let me start putting in my little parenthesis, okay, minus then this is equal to 0. So that'll represent a potential fall. So it's going to be 2.5 I2, all right. And then we're going across this battery, we're going from a negative to a positive. We're increasing in potential, so that's going to be an 18 over there, right? We already did that basically. And then here we're going to have another fall in potential since we're traveling with the current, so we're going to put that in a potential falls category, so that's going to be 0.5 times I2, all right? And now we're going to go over this way. Now notice we're moving with I1 now. We're moving in the direction of the stated current here, so therefore that's going to represent another potential fall. All right, so I realize that it's only going to be an 18 over here, so I'll move that in. And maybe we'll move this over a little bit, create a little more space. And what we're going to need to do then is plug in 6 times then I1. All right, 6 times I1. All right, great. Now simplify it if you can. So we got some like terms in there, right? So we can combine this, these I2s, and we're going to get 3I2 plus then 6I1. And that's going to be equal to 0. All right, and distribute the negative now, if you like. So it's going to be 18 minus then 3I2 minus 6I1, and that's all equal to 0. All right, so we got our 2 loop rules. Now, last but not least, we're going to do a junction rule. Okay, junction rule is very simple. Basically, junction rule now, instead of actually, I'll leave up the potential, the loop rule, because this is the loop rule. Junction rule is basically this now: the sum of all the currents incoming, right, or inflow, sum of all currents inflow into a junction. So I'll just write in, right, inflow, minus then all the currents flowing out of a particular junction must equal 0. Now, what's a junction? A junction is just like a crossroads where you can go multiple ways, right? There's only 2 junctions in this problem. It's going to be here, and it's going to be here. All right, so let me clean this up a little bit. Just get rid of this loop. So it's either going to be at this junction, that's one junction, that's another junction, right? There's multiple ways the currents can flow. So it doesn't actually matter which one you're going to pick, because they're all going to talk about I1, I2, and I3. You don't need both of them. You just need to pick one. It does not matter which one you choose. Don't overthink it. All right? So maybe what we'll do is I'll choose A. I don't know. You could choose E. It does not matter at all. But if I look at A, right, and you have your stated currents of I1 coming in and I2 and I3 going out, then what that means is my formula would look like this. The currents flowing in is I1. The currents flowing out now is going to be I2 plus I3. And the reason why is because it's the sum of all the currents flowing out, right? This is kind of in parentheses. It's the same idea as what we just did over here. You see how easy that is? And now this is just equal to 0. Okay, so now we can clean this up if we wanted. So maybe just do I1 minus I2 minus I3 is equal to 0. All right, we have all the formulas we need to solve this now. Okay, so like I said, usually you got like 2 kind of loops here. You'll use 2 loop rules, 1 junction rule. We should be able to solve. So now let's get rid of all this. By the way, the physics is over. There's no more physics. It's just math now, okay? And algebra. So the way to do this is to realize or take a step back, and I want you to look at these 2 formulas, okay, these 2 loop rules we applied. What variable do they have in common? They have an I2 in common, isn't that right? This is in common with this? Okay, so what you're going to do is whatever variable you have in common between these two loop rules will be the variable you will not be solving for in this equation and in this equation. In other words, what I'm going to do is I'm going to solve this equation for I1. And I'm going to solve this equation for I3. Watch what that allows us to do then. Okay, you'll see in a second. So let's take the 18 minus 3 I2 minus 6 I1 is equal to 0. Solve that for I1. All right, so we're going to now, right, we're going to subtract the 18. I'm going to go through this a little quicker. Subtract 18, you're going to add the 3 I2. So you're going to be left with 6 I1 is going to be equal to 3 I2 minus 18. And then you're going to divide out the 6, negative 6 from both sides, right? So it's going to be I1 equals then 3 I2 minus 18 all over negative 6. Leave that alone, okay? Leave it alone. Let's put it maybe on down here, all right? Now what you're going to do is you're going to do the same thing, okay, for the other equation. Remember, you're not going to solve this for I2, you're going to solve it for I3. So let's write it down. 2I3 minus 3I2 minus 27 is all equal to 0. So solve that for I3, so it's going to be 2I3 is going to be equal to, you're going to add this on over, add this one on over, so it's going to become 3I2 plus then 27. Divide both sides by the 2. All right, so what do we got? So we got I3 here, and that's going to be equal to 3I2 plus 27, all then divided by 2. So when we now take a step back, let's see what we've done. We have an equation here, solved for I3. So what that means is I can take this value and plug it into this formula, right? This is the junction formula. What I'm then going to do is I'm going to take this value of I1, because that's what I1 is equal to, and I'm going to plug it in for I1 here. Then take a step back and realize what we've just done. I have an equation here with 3 unknowns, but now I will have an equation with only 1 unknown, because in place of the I1, I'm going to have this term that has an I2 in it. Then this is an I2. And then in the term of I3, I now have this thing with an I2 in it. So we're all going to have just I2s in there now. All right. So now that is solvable. And that's why we needed to do this. Okay. So let's write down I1, but instead of I1, I'm going to plug this whole thing in, right? So this is going to be 3I2 minus 18 all over negative 6. And then that is going to be then subtracted by I2, which we're just going to leave alone because, there's nothing to plug in. It is just I2. And then minus now, careful with the parenthesis here. We're going to need I3, which is going to be 3I2 plus 27 all over then 2. Okay? And that's all equal to 0. All right. So now let's get rid of this stuff. All right. And now let's see what we can do in solving. All right. So now maybe let's start distributing this term to each. All right, so here we're going to come up with now a negative 0.5 I2, and then we're going to distribute this over there. So that's going to be now a positive 3. This still stays a minus I2. Minus, then keep your parenthesis here for now. 3 over 2, right, is basically going to be 1.5 I2, plus then the 27 over 2, which is basically 13.5, and that's still equal to 0. Now what I'm going to do is I'm going to distribute this negative term. All right, so it's going to be negative 0.5 I2 plus 3 minus I2 minus 1.5 I2 minus 13.5. And that's equal to 0. Now we're going to combine some like terms. So notice here I have an I2, here I have an I2, and here I have an I2. So they're all subtracted, so it's kind of like adding them together, right? Just keeping the negative sign. So this is a negative 1.5, this is a negative 1, and this is a negative 0.5. So that's going to have a value then of simply just negative 3 I2. And then I'm going to combine my positive 3 with my negative 13.5, and that'll come out to be negative 10.5, and that'll be equal to 0. So now what we got to do is go ahead and bring that 10.5 on over to that side. So we're going to have negative 3 I2 is going to be equal to positive 10.5. Divide both sides by negative 3. And we're going to realize that I will work out to be, let's see, I is going to be 10.5 over negative 3. And negative 3.5. All right. So now I2 is negative 3.5 amps. Now what that tells me, remember current, right? In reality, it's either you got some current or you don't have any current, right? The negative current just means that the direction is opposite to what we had stated it is. So in other words, I2 was kind of guessed at, right? It was guessed that it flows around the circuit in a clockwise fashion. But in reality now, since we calculated a negative value for it, the reality of the situation is that I2 actually flows the other way. But that's no big deal. That's okay. It doesn't mean that anything was wrong. It just means that the guess that was made at the beginning saying that I2 goes this way isn't right. Okay? It goes the other way. No big deal, though. That's totally fine. Now, what this allows me to do is this now allows me to solve for another variable, right? Now, remember that each of these terms here, right, this was equal to I1, and this whole thing here inside was equal to I3. So now what I can do is I can solve for the missing pieces, all right? So let's choose one of them. Doesn't matter which one. Maybe I'll choose the I1 to solve for. So I1 is equal to 3I2 minus 18 all over negative 6. Plug in now your negative 3.5 amps in there, minus 18 all over negative 6. I'm going to realize that I1 now is, let's see, 3 times negative 3.5 minus 18. Then take that all divided by that negative 6. Works out to be now positive 4.75. Great, 4.75 amps. All right. That is I1. Now the current's positive. All that means is that I1 that's stated here in the problem is pointing in the correct direction. It is going to the, it is going to the left. Okay, that's all it means. And we're going to put that up there. Great. And now we can solve for I3. You can do this in a couple of ways. The easiest way might be to use this formula. So we got I1 minus I2, right? I1 minus I2 minus I3 is going to equal 0. So we realize that I3 will simply be equal to I1 minus I2. And then we simply plug in the values. I1 was 4.75 minus then a negative 3.5. And here we have now I3 being equal to 4.75 minus a negative 3.5. So 8.25, right? 8.25 amps. All that tells me now is that the current is pointing in the right direction in the picture. All right. So those are now the answers. So basically, if I had to, take an overview of this circuit, the current here, I2, is now flowing in the direction I already stated. The current I1 is flowing to the left there. And then I3 is going still in the counterclockwise direction on the bottom. But everything now makes sense. If we look at this particular junction, let's say, right at point A, notice how there's current of I1 flowing in, and then there is, there's current of I1 flowing in, and also now I2 flowing in, and I3 is flowing out. So it still makes sense, and then you can analyze E, it still makes sense. So guys, thank you so very much for tuning in. I really appreciate it. Please, if you can, remember to subscribe. It helps us out tremendously. And tell your friends too. That also helps a lot. All right. We appreciate it. Thank you. And we'll see you soon. Take care.